Greetings, everybody. This video is going to cover one-dimensional motion with constant acceleration in the y direction. And we're going to focus, in the interest of time, we're going to focus on a particular type of problems called free fall. And the definition of free fall is an object can be, um, it can be, and remember, it's one-dimensional motion in the y direction. And free fall means that the object moves only under the influence of gravity. So we neglect air resistance and anything else. So it moves only under the influence of gravity. So we use y to indicate the distance because it's motion in the y direction, something moving straight up and straight down. Now for the acceleration due to gravity, the standard symbol makes sense as a lowercase g. Now remember, gravity always acts in the y direction. So we don't want to overthink it. We're not really getting a whole new set of equations. We're going to take the 1D x equations and we're just going to replace x with y and a with negative g. Why negative g? Because gravity always acts straight down. So we're going to just take the 1D kinematic equations. Wherever we see the variable x, replace it with a y. Wherever we see the variable a, replace it with a negative g. Well, free fall can actually be three things. It can be the initial speed can be zero, meaning the object is dropped from rest. Vi could be positive, meaning the object is thrown straight up, i.e. thrown up in the positive y. Or Vi could be negative, meaning the object is thrown straight down. So here in the first sketch, that's the case where Vi, the book uses V naught for the initial speed instead of Vi. I like I and F, but I for initial. But don't let that confuse you. That's in the language of math and physics. You'd read that as V naught, meaning the initial speed. But I use I for initial. I'm not smart enough to do the V naught. But here, this is the case. This is case 2, where Vi is positive. But notice A is negative. And the numerical value of G, I should have mentioned it. In MKS units, the magnitude, the value of G is 9.80 meters per second squared. But it's always negative because gravity always acts in the negative y. So again, here's the case where Vi is positive. Here's the case where Vi is negative. And then if it's dropped from rest, obviously Vi would be 0. Well, here I've written the one-dimensional equations in the x direction. And we're simply going to replace wherever we see an x, replace it with a y. Wherever we see an a, replace it with a negative g. So we get the following free fall equations. And again, 1 through 4, the way I write them, in the order in which I write them. So that's equation, again, from top to bottom, equation 1, 2, 3, and 4. And again, all I've done, I haven't done anything. I've just taken these 4 equations, replaced x with y, and replaced a with negative g. All right, well, let's look at an example. Well, this is out of the OpenStax text. It's chapter 2, number 41. And I want to calculate the displacement and velocity. In other words, I want YF and VF at these half-second intervals, starting at times of 0.5 seconds, 1, 1.52, 2.5. And it's for a rock thrown straight down, i.e. it's this case. Vi is negative. So it's for a rock thrown straight down with an initial velocity of 14 meters per second, and it's thrown. There's this bridge in New York City called the Verrazano Narrows Bridge. And this bridge is 70 meters above the water. Well, just like the previous examples, let's look at what we're given. Well, we are given Vi, remember, Vi is negative 14y, rock thrown straight down. Okay. Y initial is 70. How come? Well, that's the height of this bridge. The bridge is 70 meters above the water. It's being thrown from this bridge, i.e., from an initial height, a yi, of 70 meters. And then we're going to just solve it for the times of 0.5 seconds, 1 second, 1.5. So we're just doing the same thing 5 times. And the problem is asking for displacement and velocity, i.e., I want YF and VF. Well, I'm going to do the first 3 times. I'll do A, B, and C, and you all can do D and E. Okay, so let's do YF first. Well, YF, I could probably, let's look at the 4 equations. Well, I can use equation 1. I can't use equation 2 because YF is not in equation 2. Well, you could try equation 3 because there's a YF there. And you could try equation 4 because there's a YF. But why do I not want to use 3 and 4? Well, notice I don't know VF. See here, I don't know VF. I don't know VF. So 3 and 4, let's toss them out. Obviously, I can't use 2, so I have to use equation 1. So let me use equation 1 to get YF. Well, that works. What is YI? YI is 70. What is VI? Minus 14. G, we know the magnitude of G is 9.8. Remember, the minus sign is right there because I replaced A with minus G. So that the minus G, that's where the minus sign goes, right where the plus sign is. All right, so I'm going to use equation 1 to get YF. So YF is YI plus VIT minus 1/2 dt squared. Well, let me go ahead. Now, YI is never going to change. So let me just go ahead and use this equation for, again, A, B, and C. So for 0.5 seconds, 1 second, and 1.5 seconds. Well, so YI plus VIT minus 1/2 gt squared. Well, notice, so YI is 70. So no, 70, 70, 70. Now notice right here, 70 minus 14 meters per second times 0.50 seconds. Remember, VI is negative. So that's why I have to have a minus right there. Because remember, VI could be 0, could be positive, or negative. So remember, VI is negative. So then, and then minus 1/2 gt squared, so minus, well, 1/2 g, this is a nice shortcut, 1/2 g is 4.90 meters per second squared. So here's my minus sign, minus. And then here's my, in the green, that's my 1/2 g. And then, t squared, we're starting with 0.5. So plug in the numbers, you get 61.8 meters. Then, again, same thing, only now replace t with 1 second. And you get 51.1 meters. Notice it's getting closer and closer to the water. Now, so you get the idea. Now, what about VF? Well, again, probably the easiest equation to use for VF is equation 2. Because I know VI, I know G, and I'm given the times. So I'm just going to use equation 2 and just plug in the various times. So again, VF is equal to VI minus GT, but just like, again, VI is negative, so you have this negative sign out front. Again, so minus 14 meters per second minus G times T, well, minus G, again, G is 9.8 meters per second squared. Again, starting off with a time of 0.5 seconds, then 1, then 1.5. So notice you get minus 18.9, then minus 23.8, minus 28.7 meters per second. In other words, it's speeding up in the negative sense. It makes sense. As it's falling, the acceleration due to gravity is causing it to speed up. Just it's falling faster and faster. Okay, good, we're at 9 minutes. Now let's look at the second problem. Well, there's one thing. For an object in free fall, if the initial speed is positive, then when it hits its maximum height, v is always equal to 0 at the maximum height. Because if vi is positive, what happens is it's going to go straight up, As it's going up, it's slowing down. Eventually, it's going to come to a stop, and then gravity is going to cause it to then fall back down. So the maximum height, if VI is positive, the max at max height, V is always zero, as indicated by this sketch right here. Well, let's look at this problem. A baseball is hit so that it travels straight upward after being struck by the bat. The bat is 1 meter above the ground when the batter hits the ball, i.e., Y initial is 1 meter. A fan observed, somehow this fan has a stopwatch with him, a fan observed that it takes 3 seconds for the ball to reach the max height. I want to know in part A the initial velocity of the ball, VI. Part B, I want the maximum height of the ball, i.e. YF at the max height. Well, what are we given? Well, we know YI is 1 meter because the bat is 1 meter above the ground when the baseball player hits the ball. He hits it straight up. It leaves the bat with a VI going straight up. We know at the max height V is 0. And we know that according to this fan, it takes 3 seconds to reach the max height. So initial velocity of the ball, easiest equation is probably equation 2. VF equals VI minus GT. So let me go ahead. We know that V is equal to 0 at the max height. Use equation 2 to get VI. General equation, VF equals VI minus GT. Why is VF 0? Because at the max height, the speed is 0. So VF is 0 at the max height. So 0 equals VI minus GT, or VI equals GT. And plug in the numbers. Again, G is 9.8 meters per second squared. The fan said that we know from the fan, T is 3 seconds. 9.8 times 3 is going to give you 29.4 meters per second. The max height, in other words, I want Y final. Y initial is 1. The bat is 1 meter above the ground when he hits the ball, goes up. At Y final, I want Y final. What is that height? Y max or Y final? Well, Y final, this is equation 1. Whenever you want YF, usually start with equation 1. And you get YF equals YI plus VIT minus 1 half GT squared. Plug in the numbers, and you get 45.1 meters. Now, something to think about. I didn't write this down, but it's something to think about. Could you use kinematic equation 4 to get Y max? Well, sure, because you know at the max height, V final 0. So you could use equation 4 to get Y max, i.e. Y final. It's something to check. See if you get the same answer. I guarantee you will. But anyway, so that's free fall. On exam 1, there's one question on free fall. It's a very straightforward question. Let me go ahead and stop this video and save it. They do tend to get pretty large. I'm going to try to keep the videos a little bit shorter. Go ahead and stop this. And